Most walls are built to keep things out. The walls in this video were built for the opposite reason, to keep something in. I'm counting down 10 walls, barriers, and containment systems designed to hold back lava, disease, radioactive water, plasma hotter than the sun, and in one case, an idea. Starting with number 10. Number 10, Japan's lava diversion walls. Japan sits inside the Pacific Ring of Fire. It has over 100 active volcanoes, and some of them don't give much warning. Sakurajima, a volcanic island in Kagoshima Bay in the south of the country, has erupted more than 1,000 times in the last 100 years. Not metaphorically active, actually erupting regularly, close to a city of 600,000 people. So Japan built walls to argue with it. Not to stop lava. You can't stop lava. Lava is molten rock moving at the temperature of a furnace, and it goes where gravity tells it to go. What you can do is negotiate. You can build concrete barriers and channels on the flanks of the volcano that redirect the flow, steer it away from populated valleys, and buy the people below enough time to get out. That's what Japan did. And not just at Sakurajima. The diversion walls on Sakurajima and on slopes across Japan are reinforced concrete structures, some of them up to 20 meters tall, roughly the height of a 6-story building. They're not dams. They don't seal anything. They're more like concrete arguments. If the lava comes this way, would prefer it went that way instead. The walls are designed not simply to resist, but to redirect. What makes this entry the starting point for this list is how visible the intent is. Most containment engineering hides itself. Nuclear containment domes look like buildings. Frozen soil barriers look like nothing at all. But these walls sit right there on the mountainside, in plain sight, and what they're doing is completely legible. They're waiting. The mountain hasn't moved yet, and the walls are already in position. Kagoshima has ash evacuation drills. Residents keep helmets in their homes. And on the slopes above the city, the concrete walls stand in rows, angled to catch whatever the mountain decides to send down. There's a version of this that sounds like a losing battle. Humans stacking concrete against a geological process that has been running for millions of years. But that framing misses the point. Japan is trying to win. It's trying to buy time, redirect force, and keep people alive when the mountain moves. The walls aren't a solution. They're a negotiation that has to be renewed every generation. Sakurajima has been erupting since long before the city existed. It will be erupting long after. The walls on its flanks aren't there to stop it. They're there to tell liquid rock where it is and where it is not allowed to go. And so far, that conversation is ongoing. 9. The Dingo Fence. 3,488 miles long. To put that in terms you can feel, it's longer than the distance from New York to London, with several hundred miles left over. It runs from the cliffs of the Great Australian Bight on the southern coast, cuts northeast through the red interior, and terminates near the town of Jimbor in Queensland. It crosses 3 states. It has its own maintenance patrol, a team of people whose entire job is to drive its length and fix whatever broke since the last pass. It is the longest fence on Earth, and it was built to keep something in. Not quite. The framing matters here. The Dingo Fence, officially the Australian Wild Dog Barrier, fence, wasn't built to keep dingoes contained in the way a cage contains an animal. It was built to keep them out of the southeastern sheep grazing country, but the effect is the same as containment. On one side of the fence, dingoes. On the other, sheep. The fence is the thing enforcing that arrangement, and it has been doing so since the 1880s, when the various state fences were gradually consolidated into one continuous barrier. The fence itself is steel mesh, about 1.5 meters tall, with a wire overhang at the top and, in some sections, a wire skirt buried in the ground to stop animals digging under. It's not electrified along most of its length. It doesn't need to be. The dingo is a smart animal, but it hasn't figured out how to open a gate, and the fence has no gates in the sections that matter. What it has instead is inspectors. The dingo fence is maintained by state governments and local landholders, and sections of it are checked regularly by people driving along its length in 4-wheel drives, looking for breaches, a washed out section, a tree fallen across the wire, a hole something dug overnight. When they find one, they fix it. This has been the arrangement for over 100 years. The results are measurable. On the northern side of the fence, dingo populations are healthy and largely unmanaged. On the southern side, sheep losses to wild dog predation are significantly lower than they would be without it. Studies comparing land on either side have found stark differences in both predator populations and the ecosystems they regulate. The presence or absence of dingoes cascades through the food chain in ways that are still being documented. But yeah, the fence has its critics. Ecologists have pointed out that dingoes play a role in controlling kangaroo and rabbit populations, and that excluding them from the southern rangelands has had consequences that weren't anticipated when the fence was built. The land on the dingo-free side has changed. Not always in the ways the fence's builders intended. The fence doesn't know any of that. It just stands there, crossing gibber plains and red sand dunes and dry creek beds, holding a line that a government drew across a continent in the 19th century and has been paying to maintain ever since. 3,488 miles, checked by hand, repaired by hand, section by section, year after year, for over a century. It's a line drawn across a continent, and both sides of it are still arguing about whether it should be there. At number 8, BSL-4 laboratories. Somewhere within a few hundred miles of where you're sitting right now, there's probably a building that contains some of the deadliest pathogens on Earth. Not probably in a loose sense. There are roughly 60 Biosafety Level 4 laboratories operating globally, spread across North America, Europe, Asia, and Australia. They hold Ebola, Marburg, Nipah, Lassa fever. Pathogens for which there is no approved cure and no approved vaccine, housed in facilities that look, from the outside, like unremarkable office buildings or university annexes. The containment is not in the walls. That's the thing most people get wrong about BSL-4 facilities. Not thick concrete, not reinforced steel. The primary containment mechanism is air, specifically the direction air moves. Inside a BSL-4 lab, the air pressure is maintained at a level slightly lower than the surrounding building, which means that air flows inward through every seal, every door crack, every imperfection in the envelope, rather than outward. If something breaches, the airflow pulls contamination in, not out. The building breathes inward, continuously, by design. The architecture enforces this. A BSL-4 facility is a building within a building. The inner lab sits inside an outer shell, separated by a series of interlocking zones, each one at progressively lower pressure than the last. To move from the outside world into the inner lab, you pass through multiple pressure transitions, each one a step deeper into negative space. To leave, you pass back through them in reverse. And you do not leave in the clothes you arrived in. Personnel working inside wear positive pressure suits, full body enclosures with their own filtered air supply connected to the ceiling by coiled yellow air hoses. The suits are pressure tested before each entry. Workers shower in chemical solution before removing them. The air exhausted from the inner lab passes through multiple stages of HEPA filtration before it reaches the outside atmosphere. Liquid waste is heat sterilized on site. Solid waste goes into autoclaves, pressure chambers that use superheated steam to destroy biological material before it leaves the building. Every surface, every tool, every sample container is treated as a potential vector. The protocols are not precautionary. They're mandatory, documented, and audited. A researcher who skips a step isn't being careless. They're committing a breach that triggers facility-wide response procedures. The physical walls of a BSL-4 lab are reinforced and sealed, yes, but the walls aren't the containment. The containment is the system. The pressure differentials, the filtered exhaust, the chemical showers, the interlocking airlocks, the suits, the protocols, the culture of paranoid precision that every person in the building carries with them every time they enter. There are pathogens in those labs that, if released into a dense urban population, could cause outbreaks that would be extraordinarily difficult to control. The researchers who work with them know this. The facilities are designed around that knowledge. The deadliest things on Earth are held in check not by thickness or by strength, but by pressure, airflow, and obsessive life or death attention to detail. 7. The Fukushima Ice Wall. On the 11th of March 2011, A magnitude 9 earthquake struck off the Pacific coast of Japan. The tsunami it generated reached the Fukushima Daiichi nuclear power plant within an hour. It knocked out the backup generators. Without power, the cooling systems failed. 3 reactors melted down. The immediate crisis took weeks to stabilize. The contamination problem took years to even define. And one specific part of that problem, groundwater, turned out to be almost impossibly difficult to solve. Here's the issue. The Fukushima site sits on a hillside. Groundwater flows naturally downhill through the ground beneath the plant, and as it passes through the contaminated soil and building foundations, it picks up radioactive material. Then it keeps moving toward the ocean. In the years after the disaster, Tokyo Electric Power Company estimated that somewhere around 300 tons of contaminated groundwater was flowing through the site every single day. 300 tons. That's the weight of roughly 250 standard cars in water moving through a nuclear disaster zone daily. The solution they eventually settled on was to freeze the ground, not the water, the ground itself. In 2016, after years of planning and construction, TEPCO activated what's known as the Landside Impermeable Wall, a frozen soil barrier surrounding the damaged reactor buildings on 3 sides. 1,571 pipes were driven into the earth around the site, each one circulating coolant chilled to minus 30 degrees Celsius. The soil between the pipes froze solid, forming a continuous underground wall of frozen earth roughly 1.5 kilometers in total length and about 30 meters deep enough to reach the impermeable rock layer below. The visual is strange. From the surface, you see almost nothing, just a grid of pipe heads emerging from the ground, connected by insulated tubing running to refrigeration units. Below ground, the earth has been transformed into something that behaves like concrete, not solid rock, not poured material, frozen dirt, held in that state by machinery that runs without stopping. The cost of keeping it running is approximately $30 million per year, just for the electricity and maintenance to keep the ground cold. The barrier doesn't generate anything, it doesn't clean anything, it just holds. It keeps uncontaminated groundwater from flowing into the site from the uphill side, and it slows the movement of contaminated water toward the ocean on the downhill side. It has reduced the daily flow of contaminated groundwater significantly since activation, though the site still requires ongoing water management. Contaminated water that accumulates inside the barrier has to be collected, stored, and treated. That process has generated over 1 million tons of treated water, which became its own international controversy when Japan announced plans to release it gradually into the Pacific. But yeah, the wall itself, the frozen ring, is a piece of engineering that has no real precedent at this scale. Frozen soil barriers exist in mining and construction, used temporarily to stabilize ground during excavation. They're not normally permanent infrastructure. They're not normally the primary containment strategy for a nuclear disaster site. They're not normally expected to run for decades. If the refrigeration fails, the wall melts, the ground thaws, the water moves. A frozen ring of dirt in Japan, kept solid by pipes and pumps, holding back water that nobody can touch. Nuclear reactor containment buildings. Number 6. Every operating nuclear power plant in the Western world sits inside one. From the outside, it looks like a dome, a smooth, curved structure of reinforced concrete rising anywhere from 40 to 60 meters above the ground, roughly the height of a 15-story building, with walls that are typically somewhere between 1 meter and 2 meters thick. The dome is not the reactor. It's not the cooling system. It's not part of how the plant generates electricity at all. It's there for one reason. If everything else fails, the dome is what's left. The containment building is designed around a specific scenario, a loss of coolant accident in which the reactor core overheats and begins to melt. When that happens, the fuel rods degrade, radioactive gases are released, steam pressure builds, and in the worst cases, hydrogen gas accumulates to levels where it can ignite. The containment building has to hold all of that, the pressure, the heat, the gases, the fission products, inside its walls while the situation is brought under control, or until the decay heat drops to manageable levels. The walls are not simply thick, they're engineered. Steel-reinforced concrete with a steel liner on the interior surface, designed to remain structurally intact under internal pressures that would rupture an ordinary building instantly. The dome shape is not aesthetic, it's structural. A curved surface distributes pressure more evenly than a flat one, the same principle that makes an egg harder to crush than a box. On the 28th of March, 1979, the containment building at 3 Mile Island Unit 2 in Pennsylvania got its real-world test. A loss of coolant accident caused a partial meltdown of the reactor core. Radioactive gases and steam built up inside the containment structure. Hydrogen gas accumulated and ignited. A small explosion contained entirely within the building. Radiation levels inside the containment spiked to levels that were immediately lethal. Outside the containment building, radiation releases were measurable, but according to subsequent studies, resulted in very low doses to the surrounding population. The dome held. Not because nothing went wrong. Everything went wrong. It held because it was designed to contain a meltdown, not prevent one. Prevention is the job of the cooling systems, the control rods, the operators. The containment building's job only begins when all of those have failed. If you're enjoying the video, drop a like and a comment. It really does help the channel out. And we're not done. The next entry on this list is a wall designed not to contain a physical substance at all, but something considerably harder to hold. The design has evolved since 3 Mile Island. Modern reactors incorporate passive containment cooling systems, designs that don't require pumps or operator action to function, relying instead on gravity and natural convection to keep the containment structure cool in an emergency. Some newer designs use a double containment structure, one dome inside another, with the space between them maintained at negative pressure so that any leak from the inner containment is drawn inward rather than outward. The containment building is the last engineered barrier between a reactor accident and the surrounding environment. It is designed to be used. It is designed to be needed. The engineers who specified its wall thickness and its steel liner and its dome geometry were not being optimistic about what might happen inside a nuclear power plant. They were being precise about it. The concrete and steel dome did exactly what it was designed to do. 5. A DX Florence, Fremont County, Colorado. In the desert of southern Colorado, about 100 miles south of Denver, there's a federal prison that most people will never see the inside of. And that's entirely the point. The Administrative Maximum Facility, known as ADX Florence, opened in 1994. It is the only federal supermax prison in the United States. It holds somewhere around 300 to 400 inmates at any given time, in a facility built for one specific purpose: to contain people the Bureau of Prisons considers too dangerous, too disruptive, or too influential to be held anywhere else. The cell is 7 feet by 12 feet, roughly the size of a parking space. Inside that space, a concrete bed, a concrete desk, a concrete stool, a toilet, a sink, and a shower. All fixed. All concrete. The window is 4 inches wide, narrow enough to prevent any view of the surrounding landscape, wide enough to admit a sliver of natural light. Inmates in the most restrictive units spend 22 to 24 hours a day in that cell. Meals come through a slot in the door. Exercise happens alone in a slightly larger concrete enclosure, sometimes described as a dog run, an outdoor cage open to the sky with no equipment and no other people. The walls at ADX are not primarily designed to prevent physical escape. Physical escape from a modern maximum security prison is already extraordinarily difficult. What ADX is specifically engineered to prevent is something harder to define and harder to contain: influence. The people held at ADX Florence include individuals convicted of terrorism, espionage, organized crime leadership, and multiple murders of federal officers and other inmates. The roster has included Zacharias Moussaoui, convicted in connection with the September 11th attacks, Ramzi Youssef, who planned the 1993 World Trade Center bombing, Ted Kaczynski, the Unabomber, who died there in 2023, Joaquin Guzman Loera, El Chapo, held there after his extradition from Mexico. These are not people the system simply wants to punish. They're people the system has determined cannot be allowed to communicate freely, organize, recruit, or direct operations from inside a conventional prison. The walls of ADX are designed to sever those connections. No congregate activities, severely restricted correspondence, monitored phone calls, limited in number and duration. The architecture enforces isolation as policy. The facility has faced sustained legal challenges over its conditions. Former inmates and civil liberties organizations have argued that the level of isolation constitutes cruel and unusual punishment, citing documented psychological deterioration among long-term residents. The courts have largely upheld the facility's practices, though conditions have been modified over the years in response to litigation. The Bureau of Prisons describes ADX as a last resort, a place inmates are sent when they've demonstrated they cannot be safely managed in any other federal facility. Some inmates have been transferred out after years of compliance with prison rules. Others have been there for decades. But yeah, the physical structure is only part of what makes ADX what it is. The walls are thick, the doors are heavy, the sightlines are controlled, and then layered on top of all of that is the procedural architecture, the restrictions on communication, the limits on human contact, the careful management of every interaction an inmate has with the outside world. The most dangerous people in the federal system are not just locked up behind the concrete walls in the Colorado desert. They're removed from the world entirely. The New Orleans levee system. Number 4. So, the city of New Orleans sits in a bowl. That's not a metaphor. It's the actual topography. The city is surrounded on 3 sides by water: the Mississippi River to the south, Lake Pontchartrain to the north, and Lake Borgne to the east. Much of the city sits below sea level. Some neighborhoods sit as much as 6 to 8 feet below the surface of the lake that borders them. The ground itself is subsiding, compacting, and sinking slowly, year by year, as the sediment that built the Mississippi Delta continues to settle. New Orleans has been there for about 300 years. The levees have been there almost as long. The first earthen levees along the Mississippi were built in the early 18th century, not long after the city was founded. They were modest, a few feet of compacted earth along the riverbank, enough to hold back seasonal flooding. Over the following 2 centuries, as the city grew and the Army Corps of Engineers took over flood control management, the system expanded into something far more complex. Hundreds of miles of earthen levees, concrete flood walls, pump stations, and navigational locks forming a near-continuous barrier around the metropolitan area. By the early 2000s, the system stretched for roughly 350 miles. It was the most extensive urban flood protection system in the United States, and it had a problem that engineers had documented for decades. Significant portions of it were not built to withstand a major hurricane, making a direct hit on the city. On the 29th of August, 2005, Hurricane Katrina made landfall near the Louisiana-Mississippi border. The storm surge it pushed into Lake Pontchartrain and the surrounding waterways exceeded the design tolerances of multiple sections of the levee system. Flood walls failed. Earthen levees were overtopped and eroded. Within hours, water was moving through breaches in more than 50 locations across the system. 80% of New Orleans flooded, some neighborhoods under 10 to 15 feet of water. 1,833 people died across the Gulf Coast, the majority in Louisiana. Entire communities were submerged for weeks. The damage to the city and surrounding region was estimated at over $125 billion, making Katrina one of the costliest natural disasters in United States history. The failure was not purely natural. Subsequent investigations, including a major report from the American Society of Civil Engineers, found that the levee system had failed in large part due to engineering and design deficiencies. Walls built on inadequate foundations, sections constructed to inconsistent standards, a system that looked continuous on a map but was riddled with weak points in practice. The reconstruction took the better part of a decade and cost approximately $14.5 billion. The Army Corps of Engineers rebuilt and upgraded the system, raising levee heights, replacing flood walls with stronger designs, installing massive surge barriers at the mouths of key waterways. The Lake Borgne surge barrier, completed in 2013, is one of the largest floodgates in the world. A steel and concrete structure stretching nearly 2 miles across, designed to block storm surge before it reaches the city. The rebuilt system has been tested by subsequent storms and has performed significantly better than its predecessor. But the underlying geography hasn't changed. The city is still in the bowl. The ground is still sinking. The Gulf of Mexico is still rising. The levees, the flood walls, the pump stations, the surge barriers, all of it has to work perfectly, continuously, and indefinitely to prevent geography from doing what geography has been trying to do for 300 years. Fill the bowl. 3. The Three Gorges Dam, Hubei Province, China. Built between 1994 and 2006, the Three Gorges Dam on the Yangtze River is the largest hydroelectric dam ever constructed. The numbers are almost difficult to process in sequence, so take them one at a time. The dam wall itself is 181 meters tall, about the height of a 60-story building, and 2,335 meters wide. That's wider than the island of Manhattan is at its broadest point. The structure contains 27 million cubic meters of concrete. To picture that, the Hoover Dam, which most people would describe as a large dam, contains roughly 3 million cubic meters. The Three Gorges Dam contains 9 times that volume. The reservoir it created stretches 600 kilometers upstream into Chongqing Municipality, roughly the distance from London to Edinburgh, flooded. 600 square kilometers of land went underwater. 28,000 square kilometers of watershed were affected. 1.3 million people were relocated. Entire cities, towns, and villages dismantled and rebuilt on higher ground before the waters rose. And then there's the rotation figure. When the reservoir filled, the redistribution of that mass of water, around 42 trillion kilograms held at elevation, measurably affected the rotation of the Earth. Not by much. By approximately 6/100ths of a microsecond per day, the planet's day got imperceptibly longer. The Earth's axis shifted by roughly 2 centimeters. These are real, documented effects. The dam is large enough to have nudged the physics of the planet. The primary purpose is power generation. The dam's 32 main turbines have a total installed capacity of 22,500 megawatts, making it by a significant margin the world's largest power station by installed capacity. In a good year, it generates enough electricity to power a country the size of Canada for several months. It supplies a substantial portion of the electricity consumed by central and eastern China. But the containment function is the other half of the story. The Yangtze River has flooded catastrophically throughout recorded Chinese history. The floods of 1931 killed an estimated 1 to 4 million people, one of the deadliest natural disasters in human history. The floods of 1954 killed over 30,000. The floods of 1998 killed more than 4,000 and caused over $25 billion in damage. The dam was designed in part as a flood control structure capable of holding back floodwaters during peak flow events and releasing them in controlled volumes downstream. The reservoir can store up to 39.3 cubic kilometers of water for flood control purposes. During major flood events, the dam operators manage the water level in the reservoir to absorb the incoming surge, holding it back, then releasing it gradually when downstream conditions allow. The engineering required to build it was staggering in its complexity. The Yangtze had to be diverted twice during construction. A ship lift and a series of navigational locks were built alongside the dam to allow river traffic to continue moving through the gorge. The 5-step lock system, which raises and lowers ships through a total elevation change of 113 meters, is itself one of the largest navigational structures in the world. The dam has its critics. Seismologists have raised concerns about reservoir-induced seismicity. The weight of the water and changes in groundwater pressure can trigger earthquakes in geologically active areas, and the Three Gorges region has experienced increased seismic activity since filling. Ecologists have documented significant impacts on the Yangtze's ecosystem, including on the migration patterns of fish and on sediment transport that once replenished downstream floodplains. The dam holds all of that. The power, the controversy, the displaced million, the shifted axis, behind a wall of concrete nearly 2.5 kilometers wide. It must never, ever fail. 2. The Itier Tokamak, Saint-Paul-les-Durance, France. 35 nations are building one machine. The European Union, the United States, China, Russia, India, Japan, and South Korea, countries that agree on very little, have been pooling money, expertise, and components since 2007 to construct a device in the south of France that has never existed before at this scale. The total project cost is estimated at somewhere between 20 and 22 billion euros, making it one of the most expensive scientific instruments ever built. It is called ITR, which stands for International Thermonuclear Experimental Reactor and also deliberately means the way in Latin. What it's trying to do is contain a star, not literally a star, but the process that powers stars, nuclear fusion, the collision of hydrogen isotopes at extreme temperatures and pressures that releases enormous amounts of energy. The sun achieves this through gravity. Its own mass crushes hydrogen plasma at its core to temperatures of around 15 million degrees Celsius, and the resulting pressure is enough to force atomic nuclei together. On Earth, you don't have the sun's gravity. So to achieve fusion, you have to compensate with temperature. You have to run the plasma hotter than the sun's core. Much hotter. ITER's plasma is designed to operate at 150 million degrees Celsius. That's 10 times hotter than the center of the sun. At that temperature, no physical material on Earth can contain it. Touch it with anything solid and the material vaporizes instantly. The plasma cools and the reaction stops. So the wall is not a wall in any conventional sense, it's a magnetic field. The tokamak, the Russian-derived word for the donut-shaped magnetic confinement device, uses superconducting electromagnets to generate a magnetic field powerful enough to hold the plasma suspended in the center of a vacuum chamber, away from every physical surface. The plasma floats. It touches nothing. The magnetic field is the only thing standing between 150 million degrees and the surrounding structure. And the surrounding structure, just 1 meter away from that plasma, is cooled to minus 269 degrees Celsius. That is colder than deep space. The superconducting magnets require temperatures approaching absolute zero to function. Any warmer and they lose their superconducting properties and the magnetic field collapses. Within that single meter, the temperature drops by 150 million degrees. That is the steepest temperature gradient that has ever existed, or will ever exist in any engineered system on Earth. Hot enough to fuse atomic nuclei on one side, cold enough to freeze oxygen solid on the other, separated by a vacuum chamber wall and a set of electromagnetic fields generated by coils the size of houses. The ITER machine is not yet operational. As of the mid-2020s, the project is in its assembly phase at the site in Cadarache in southern France, where a purpose-built facility houses the tokamak assembly. The machine's components have been manufactured across the member nations and shipped to France for final assembly. A process complicated by the fact that some components are among the most precisely engineered objects ever made, and they have to fit together within tolerances of fractions of a millimeter. ITER is not designed to generate electricity. It's a proof of concept machine. Its goal is to demonstrate that a fusion reaction can produce more energy than it consumes to sustain, which no fusion device has yet achieved at scale. The target is a fusion power output of 500 megawatts from an input of 50 megawatts, a gain factor of 10. If it works, it establishes the physics and engineering basis for a generation of commercial fusion power plants that would follow. The fuel is deuterium and tritium, isotopes of hydrogen. Deuterium can be extracted from seawater. The potential fuel supply is, for practical purposes, unlimited. But yeah, none of that happens if the wall fails. Not the physical wall, the magnetic one. The invisible boundary that holds a piece of the sun in place long enough to extract energy from it. The walls of the tokamak are, in a very real sense, the walls between the present and the future. 1. The 10,000-year nuclear waste warning. Deep beneath the desert of southeastern New Mexico, about 2,000 feet below the surface, carved into a salt formation that has been geologically stable for 250 million years, there is a repository for the most radioactive waste produced by the United States nuclear weapons program. It's called the Waste Isolation Pilot Plant, YPP. It has been receiving transuranic radioactive waste since 1999. The salt walls of the caverns slowly compress around the waste containers over time, sealing them permanently into the rock. The containment works. The geology is sound. The engineering is defensible. The problem is time. The waste stored at WEP will remain dangerously radioactive for approximately 10,000 years. 10,000 years is not a planning horizon that human institutions have ever successfully maintained. The Roman Empire lasted roughly 500 years. The entirety of recorded human history stretches back perhaps 5,000 years. Whatever governments, languages, and civilizations exist 10,000 years from now will have no direct continuity with the ones that built this facility. They may have no knowledge it exists, and if they find it and dig into it, they will be harmed by what's inside. So in the 1980s and 90s, the United States Department of Energy commissioned a remarkable and genuinely strange project. Design a warning system capable of communicating danger across 10,000 years to people whose language, culture, and symbol systems are entirely unknown. The team included linguists, anthropologists, material scientists, astronomers, and architects. They called themselves the Human Interference Task Force. The physical warning system they proposed, and which has been partially implemented, is not a wall in any conventional sense. There is no single barrier. What they designed instead is a landscape of deterrence, a field of enormous granite and concrete spikes, each one up to 25 feet tall, covering the surface above the repository in a grid dense enough to make the area visually hostile and physically difficult to traverse. Not decorative, not symbolic. Designed to feel, on an instinctive level, like a place that has been deliberately made wrong. Around the perimeter, a berm, a raised earthen wall, encloses the site. Set into the berm at intervals are rooms containing messages inscribed in 7 languages: English, Spanish, Russian, French, Chinese, Arabic, and Navajo. The messages are also inscribed on granite monoliths placed throughout the site. The language is careful and strange, written to be as legible as possible to someone with no prior context. The inscriptions read, in part, "This place is not a place of honor. No highly esteemed deed is commemorated here. Nothing valued is here. What is here is dangerous and repulsive to us." And then, "This message is a warning about danger. The danger is still present in your time, as it was in ours." The panel of experts debated whether any warning system could actually work across that span of time. Some argued that any structure large enough to be visible would attract curiosity rather than deter it. That a field of enormous spikes says something significant is here as much as it says stay away. One proposal suggested doing nothing, no markers, no warning, relying on institutional records alone. Another proposed creating an atomic priesthood, a self-perpetuating order whose sole purpose was to transmit the knowledge of the site across generations through ritual and myth. None of those alternatives were adopted. The spike field and the inscriptions are what exists, or what is planned. But here's what separates this entry from every other one on this list. Every previous wall in this countdown is designed to contain something physical: lava, groundwater, plasma, flood, pathogen, a human being. The walls work by being present, by being solid, by interposing themselves between what must be kept in and everything outside. This wall is designed to contain something that has no physical form at all. Not the waste, the geology handles that. What the warning system is designed to contain is curiosity, the impulse to investigate, the human instinct, 10,000 years from now, to look at a strange landscape and wonder what's underneath it, and dig. The entire apparatus, the spikes, the berms, the inscribed rooms, the 7 languages, is a wall built against a question. Whether it will hold is something no one alive today will ever know. Don't dig here. Don't open this. If you thought these walls were extreme, wait until you see our video on the most dangerous places on Earth that are completely off limits to the public. Click here and I'll see you over there.